Hello again. Today I'll be going over how to generate DTMC transition matrices programmatically in order to get the stopping times on a given sequence of random variable results. So this is the third video in the series of videos that I've been making on this topic. On basically, it kind of boils down to like how many coin flips do you need to do before you see a sequence of, say, heads and tails, or tails tails, or heads tails heads, and so on. It's a lot more complicated than you might originally think. That's why there are 3 videos on it. But for now, let's just continue here. So in the previous video, we talked about using state machines to calculate the expected number of times we needed to flip a coin before we saw that given sequence of heads and tails. If you haven't watched that video, please do so now. It's linked in the video description, and it'll give a lot of context to this video. But one of the downsides that we saw maybe to using this approach is that we had to generate these state machines manually, which for really long sequences, like this one here of H's and T's, heads and tails, which has at least 17 states, right? Because there are 17 characters, I think. That could end up being a challenge, and it could be kind of a bottleneck in our process. So in this video, we discuss a way to generate these state machines algorithmically, avoiding the manual work of creating them by hand. And we're going to be talking about regular expressions, deterministic finite automata. So this video is kind of going to give a bit of a super trimmed down version of the first couple lectures in a class on automata theory or theory of computation. So if you have some prior experience with that, that'll be very helpful. If you don't, hopefully I'll make things reasonably easy to understand. I probably won't though, so maybe you want to do your own research and then come back just on some of the basics. And then I'll go into how we can use this knowledge really to help us generate these state machines programmatically rather than doing so by hand. So first I'll give some background knowledge again on these topics. I'll talk about creating the regular expression for a given sequence of random variable results. I'll talk about converting it into a minimized DFA, and then I'll give some examples. So as a general caveat, I'm not sure whether this works completely without fail for all inputs and random variables. I think it should, but it's just a method that in practice has worked for me. I haven't tried it on super complicated stuff, but I think it makes sense. I think it should work. I don't have like a formal proof of it, but it works in practice. So let's get into the background knowledge. So this might be a review for some. If you already know this stuff, feel free to skip ahead until you find something you don't know. So when we talk about regular expressions and automata, we talk about the empty string, epsilon, as a string of 0 length. In programming, we can represent that as just these 2 quotes. We talk about a regular expression, we mean a set of strings using literal characters, so like A or B or X or Y or 0 or 1, and the operations on these characters. So let's talk about those operations. We have 3 operations. We have concatenation, union, and the cleany star operation. So concatenation, sometimes we omit the operator sign, but when we don't, it's this little dot here. So if we have A and B as regular expressions, and by the way, this is a recursive definition, right? So A and B are also regular expressions. Then A concatenated with B, or AB, right, omitting that operator, is a regular expression which denotes a set of strings of the form A concatenated with B, where A is some string in A and B is some string in B. Next we have union, which we denote using this pipe operator. So say, again, we have A and B as regular expressions, then A union B is a set of strings from either A or B. So that's, you can have like little a, or you could have little b, but you can't have both with this A union B regular expression. And then we have the cleany star, which we denote using this asterisk. So say we have some regular expression big A, then A star is a set of strings basically of 0 or more A's. This we could also include the empty string epsilon, right? So like this would also be in A star, A, right? And then like infinitely concatenated as many times as we want, where A is a string in that big A regular expression. So let's give some examples, right? So let's talk about concatenation. If A is 0, 0, 0, right, this A is basically 0 star, right, the set of strings containing 0 more zeros, and B is 1 star, the set of strings containing 0 more ones, then A concatenated with B is going to be the set of strings containing 0 more zeros followed by 0 more ones. Should be pretty straightforward. Next, if A and B are the sets of 0 more zeros and 1s respectively like before, then the union of those is going to be either it's going to be strings containing either 0 or more 1s or 0 or more 0s, but not both, right? So you're not going to have any strings that contain a 0 and a 1. And then if A is a set of strings over, it's just a set of strings 0 or 1, then A star is going to be the set of strings of 0 more 0s and 1s. So just every possible string over this alphabet of 0 and 1. So now let's go into some regular expression examples. So here, this expression is representing the strings. This first one here is representing the strings containing an even number of 0s and any number of 1s, right? So whenever we add 0s, we add 2, right, at a time, which means that no matter how many 0s we add, we are going to get an even number. 0 is even, right, and then 2, 4, 6, 8, etc. And then we could also add any number of 1s. So we could add 0 1s, or we could add more than that. Here, this is just the set of all strings over the alphabet 0, 1. Here, this set is literally just the string, the literal string, right? 1, 0, 1, 1, 0, 1. Here we have the set of strings of length 3, right? So it's either a 0 or a 1, and then 0 or 1. Also, this is, this should be over alphabet 0, 1. And then here, this is the set of strings representing binary numbers divisible by 3. So this, I guess if you want to look into this more in depth, you can do so on your own time, but it just goes to show that regular expressions can be pretty powerful. So now, with that out of the way, let's talk about DFAs, or deterministic finite automata. So a DFA is this 5-tuple, Q, sigma, Q naught, F, and delta, where Q is a set of states, sigma is the alphabet over which we have this automaton. Q naught is in Q, right? So it's an element of our states, and it's the initial state. We have F, which is a subset of states that is a set of final states. And then we have delta, which is our transition function, where we take a state and we take a character, and then we go to another state, right? So if we're in a given state and we see a certain character when we're reading our string, then we go to the next state given by delta. So we can check whether a string is accepted by a DFA by starting in the start state and then following transitions on each character, so following delta, until the string is finished. And if we end in a final state when the string is done, then the string is accepted. Otherwise, we reject that string, and our DFA does not accept it. So as an example, let's look at this DFA. This one accepts strings with an odd number of 1s and any number of 0s, right? So we start in the start state given by this arrow. And when we see a 1, we hop over here. When we see another 1, we hop back here. When we see a 0, we just stay in the same place, right? So 0s don't really affect us at all, but 1s will change where we are from here to here and so on. So if we see an odd number of 1s, right? So if we see 1, 1, we go here. This is our accept state, you can tell because of the double circle. If we see another 1, so an even number of 1s, we come back here, right? So even number of 1s, we stay here, and odd number of 1s, we are in the accept state, which means that strings with an odd number of 1s and any number of 0s will be accepted by this DFA. So this is the regular expression for that. You can kind of see 0 star, right, like any number of 0s, and then a 1, then followed by 1, and then possibly 0s sandwiched in between there, and then another 1, and then a 0 maybe otherwise, and then any number of those. So this is the regular expression. It should kind of make intuitive sense that we have an odd number of 1s here. Now let's talk about NFAs. So non-deterministic finite automata, this should be NFA, not DFA, is a 5-tuple, basically very similar to DFAs, where everything is the same, but delta, instead of being defined as a function from Q and sigma to Q, is defined over the power set of Q. So basically, instead of we're going from one state and a character to another state, we're going from a subset of states, right? So a set of states, that's a subset of Q, and a character to another subset of states. So an NFA can have multiple states that it's in at the same time. We say that an NFA accepts a string if any of the states it's in, once the string ends, once we finish processing it, is a final state. And if none of the states that the NFA is in are final states, then we reject the string. So here's the corresponding NFA for the previous DFA. You'll note it's exactly the same because actually all DFAs are NFAs. So that should make intuitive sense, but if it doesn't, just think more. Okay, and then here's the NFA for the previous, for the regular expression 1001. So here you can tell this is much more simple than our DFA would be, because we don't have to have any like backwards loops in case anything bad happens, or in case we don't go where we want to go. We just ignore that, right? So here we have 1 and then 0 and 0 and 1, A DFA, we would need to have another 0 loop in this first state. We would need to have a transition on 1 in this state, a transition on 1 in this state, and a transition on 0 on this state. And here, this state just doesn't have any transitions at all. So in an NFA, if you were here and then you saw another thing, then I guess the instance that you would be here would die off, right, in that tree. And you would keep processing the states that you have left until you saw something. So this can make them much more convenient for creating from regular expressions, and it can also make it just more convenient in terms of looking at whether something accepts a string. But NFAs are actually more complicated to parse. Sorry, not to parse, but to calculate whether they accept strings or not, because you have to multiplex kind of like over all the possibilities you could be in. So that's something to keep in mind. So we can convert between NFAs and DFAs using the power set construction. The analog for the current state of a DFA is the set of states that we saw this set of states in an NFA, right? So in our delta transition function, we saw that in a DFA we had a single state, and in an NFA we can have multiple states at the same time. And also something to note is that in practice these conversions can be done faster than exponential time, which the power set construction is worst case exponential, but in practice we can get faster than that as long as we implement it smartly, pruning unvisitable states, et cetera, minimizing where we can. Generally we can do it reasonably quickly. So let's look at a sample power set construction, right? So here's the NFA for 0, 1. Start here, we see a 0, we go here, we see a 1, we go here, and then we accept that string. The DFA for this is a bit more complicated, right? So every state needs to have a transition on every one of the alphabets, characters in the alphabet. So here we need a 0 and a 1. If we see 1, then we die, right? Here's our death state, you can kind of think of it as. Then here, or here, we see a 0 instead of a 1, then we go to this death state. And then here, if we see either a 0 or a 1, then we go to the death state. And in the death state, we just stay there, and we never leave. So it's almost like an absorbing state in a Markov chain, if you want to think of it like that. But yeah, so this is just an example of the power set construction as far as this stuff is concerned. Basically, we look at where we are here, and then we see the possibilities, right, for every one of these. And in reality, this is not necessarily a complete power set construction. Really, this would be 8 states, because 2 to the 3 is equal to 8 in our naive power set construction. This is all the minimized version of that. If you want to see some more info on the power set construction and converting between NFAs and DFAs, I would Google that. And another thing, we might need to get our DFA minimized, right? So here we minimize this. There would be 8 states in the actual thing. So something you might want to look into is Hopcroft's algorithm for that, which is a good algorithm for minimizing stuff and reasonably easy to implement. So next, let's talk about a regular expression for a sequence of random variable results. So now that we have a good idea of how regular expressions work, and maybe a good idea of NFAs and DFAs, or maybe not, maybe you should review that. So if we want to get a DFA for a sequence that ends in some specific sequence of results, so say we have some sequence that ends in HT, then we can use this following pattern, right? So here we have sigma star, and then S, and then sigma star again, right? So here, sigma star is the set of all strings that we can create over the alphabet sigma for our DFA, and S is the sequence that we want to see. So in this circumstance, S could be HT, right? And then sigma star would be H or T star. So to get sigma star, we have all these elements, say A0, A1, etc. in sigma. Then sigma star is going to be equal to the union of all of them, and then star, right? So any number, 0 or more of any of these characters. It might seem a bit counterintuitive that we actually have this sigma star at the end of the regular expression, since we do want the sequence to end, right? We want the sequence to end in S. So why are we adding this other sigma star at the end? But this is actually required in order to get the probability 1 self-transitions in the absorbing state, right? So when we get to the end of HT, we want to just stay there and not move at all, right? So no matter what we see, we want to stay in that accepting state. So that's kind of why we have that. So let's look at this example, right? So again, say sigma's HT, heads and tails, right? And we want to see the sequence heads, tails. Then our regular expression is heads or tails any number of times, right? And then we have to see the sequence exactly heads, tails, and then no matter what, we just stay in the same state afterwards, right? So here we've got tail, right? We just stay in the same place, heads, right? This is exactly the same as the previous video in that example that we saw. And then here, heads any number of times, we're going to stay in the same place. Then tails, we're going to continue over there. right? And heads, tails, any number of times, we're just going to stay in the same place, right? So this is what the minimized version of the DFA that we get from converting the regular expression to the NFA and then NFA to DFA here. So now let's talk about conversion from a DFA to a DTMC. So we want to convert this generated DFA into a DTMC so we can get the transition matrix and calculate the expected number of steps until absorption. So for the sake of example, right, let's suppose that the coin we have is weighted. This is just, for illustrative purposes. The coin might as well not be weighted, but this is just for the sake of example to kind of demonstrate what it looks like and how we get those probabilities and add them up in the conversion process. So let's say that h is 0.7 and t, we get that 30% of the time, right? Then x will give this a random variable, kind of like a Python dictionary here, h to 0.7 and t to 0.3. And then our probability of going from this from state to this to state is going to be the sum over all the deltas in our transition function delta, right? That we go from the from state and on some character where it's equal to the to state, right? So where we go from the from state to the to state on this character C for all characters in sigma. Just want to make sure we get the difference. This is actually a summation, this sigma. This is a sigma as in like the alphabet sigma. Sorry for any confusion there. And then x sub c here, I'm going to refer to as like the probability that we see this character C given our variable, our random variable x. So like for h, so like x sub h would be 0.7, x sub t would be 0.3, right? So yeah, all right, now let's look at that example in practice. So here, t, right, we know it's going to be 0.3, h is going to be 0.7, h 0.7, t 0.3, and then ht, well, h is 0.7, t is 0.3, so we add those up and we get 1, right? That's what this fancy formula is saying down here. And then we can use this DTMC to calculate the number of expected steps before we reach the final state, either by solving that system of equations that we talked about in that previous video, or by using the formula I minus q inverse multiplied with the one vector on the substochastic transient matrix Q associated with that DTMC, which I talked about in a previous video, actually two previous videos, one where, one of the original one, and then the other one where I discussed a little bit about how we get that formula. So let's go over the summary again, right? What are the steps here? So first we wanted to create that regular expression for the sequence that we want to see. So for example, if we had ABC as our sequence over the alphabet ABC, then we would use the regular expression A or B or C star, and then A, B, C, and then A or B or C star again. Then we want to convert this regular expression into an NFA. I noticed that I actually didn't talk about this part. I'll link to some resources in the video description that go over how to actually perform this conversion. It's pretty simple, not too complicated, and it's also like a recursive conversion, kind of directly, which directly comes from how those operators work, those regular expression operators work. And then you want to convert this NFA to a DFA using something like the power set construction. Then we want to minimize this DFA using something like Hopcroft's algorithm. And then we want to convert the minimized DFA using the DTMC, using the probabilities given in the random variable definition. So using this formula right here. Okay. All right, so thanks for watching. That's it for this video. And as some caveats, remember to minimize DFAs. I didn't go too much in depth in that, but yeah, just look up Hopcroft's algorithm for more details. And also, you might need to do some work to make sure that you get your absorbing state detected correctly, right? So you want to get the one that has the one transition to itself, right? So probability 1 transitions from itself to itself. And I'll link in description to a Google Colab notebook that I use to test out a lot of this stuff. I basically copied a lot of automata functions basically from this library that I found online through Python that did stuff like minimizing DFAs, converting from regular expressions to DFAs, etc. And then I basically took that, made a little wrapper around it with some NumPy and did some linear algebra, created that transition matrix, etc. And it looks like it works pretty well, but again, I think the detection logic is a little bit iffy, so take everything with a grain of salt there. And yeah, I noticed, again, I'm sorry, I forgot to discuss how to convert from regular expressions to NFAs, but I'll link to resources in the description on that as well. And yep, so thank you for watching, and see you next time.